Let's get started. Okay, welcome to CAPP Seminar. I'm happy to introduce today's speaker, Chang Lee. He got his PhD from Case Western Reserve University in Cleveland, Ohio, in 2015. And after that, he spent 1 year with SLAC as a visiting scholar. And then he moved back to Korea with CUP at IBS for 3 years, and he has been working on the Amore experiment you're familiar with. And then in 2018, he moved to Germany to join the Planck Institut for Physics. And then currently he's working on MADMAX, the large scale experiment for axial search. So he had the chance to visit Korea this winter and give us some seminar talk, and then he will talk about the current status of MADMAX. Okay, let's welcome him.
Okay, thank you very much for the invitation and the introduction. So yeah, I'll be talking about the MADMAX experiment. So we have the president and the Planck Institut in Munich. So yeah, here is the recipe for the release recipe for the universe. We know that dark matter is thermal metal, barium matter is because of ice, and the rest of the material is mostly dark, especially the dark matter counts 1/4 of the mass energy. And the real question is, what is the dark matter? What is the state of the particle? And I found this graphics in the Quanta magazine. This lists all the possible dark matter candidates, serious candidates, including crystal winds and axions. And the key point I wanted to show you was that they used the MADMAX at the meeting experiment in the axion along with the ADS and the second course. So I guess I can go briefly about the introduction with the expert now. So we know the symmetry is broken in the universe. We see more error, and you see the Lagrangian in the CP, by the way. The theta angle here parameterized the degree of the violation, and this can have any value between pi and a because this is an angle. It's just close.
It's going to be better, but I think this is okay. Yeah.
Okay. So, but experimentally, we see the data is extremely close to 0 by measurement of the electron dipole moment. So, the question is why theta is so unnaturally small, and it's just a strong signal problem. So far, the most elegant solution for the problem comes from SI and Queen. They promote the theta angle from a constant to a dynamic field that changes over time and space. And this field breaks spontaneously and is still at A. So this becomes the maximum potential at the energy scale at A. In addition, QCD field measure. So this theta angle can oscillate around the CP tensor and make the vacuum expectation value of the theta effectively 0, solving the strong CP problem. Axion is the fluctuation of this theta, and this new particle is slightly massive because this QCD field is the same field potential. And this theta angle, the residual theta angle of the relic axion, turns out to be a great candidate for dark matter. First, because of spontaneous symmetry breaking, it interacts very weakly with the standard model particles, for example, photon, especially when the FA is pretty large. And we know experimentally FA is larger than the electrical energy scale. This production mechanism based on spontaneous symmetry breaking makes it cold, even though this is a very light mass, so it's not relativistic. And the third, this large energy scale implies that the mass of axion is very small, and it has a very long lifetime compared to the age of the universe. So in summary, the large energy scale FA implies the small mass, small coupling, and the movement. So this fit perfectly for the full dark matter candidate. And the question is, what can be the axial mass? And it depends on the scenario, but if a positive inflationary scenario, we can narrow down the mass rate a little bit. It's the inflation happens, or if the symmetry breaking happens, inflation. So this is a patches of the universe, and this arrow represents the theta angle can have any degree between pi and minus pi. The inflation happened after the symmetry breaking. The inflation can pick up any patch of the universe and go to the universe that we live in. So theoretically, any value between minus pi and pi is possible, although very small zero values. However, so this does not combine the mass range very well. On the other hand, if the inflation happened before the passive symmetry breaking, and the theta angle we observed today is simple mixture of the possible values. So we cannot have the very small theta angle, and this can better confine the axion mass. Very roughly, we expected this scenario axion mass above about 30 degrees. And this is the landscape of the axion dark matter detection in the mass versus the axion to photon coupling. And this is axion. Anything outside the line is axion like particle. And these are the current limits from the experiments. And you can see that most of the existing limits are in this range below like about 35 eV or 10 gigahertz. And this region is almost empty. So this is the beginning of the scenario that's favored by the post-inflation scenario. The reason is most of the current experiments rely on the resonant cavities for detection, and the reading of this strategy was used fantastically in the low frequency region, especially below 10 gigahertz. Well, this quickly loses efficiency at higher frequency because the volume and the signal power from the cavity is proportional to the third power of the frequency. So here is a typical example of the typical cavities, how fast their volume shrinks from the 2.5 gigahertz to 100 gigahertz. So small ones can basically fit inside the big ones. If we try to use a big cavity for high frequency, then you immediately run into the multiple impulse because this can support the much but higher order modes. So the axion will couple to this high frequency mode that cannot use it. So the question is, how can we speed up the search? And then today I'll focus mainly about how we increase the volume of the cavities without affecting the performances. So here's a cartoon image of how the cavity size shrinks in the theme of Oktoberfest, where the most blockest is. So this is the size. 1 gigahertz cavity is about the size of a 1 beer cask, and 10 gigahertz cavity is the size of a 1 glass or smaller. So we begin with the axion field. This axion, this is also named with axion mass omega A, and the frequency or the mass range of interest. This is all dark old, so we assume that our wavelength is on the order of 10 meters, so 1/2 wavelength is about 5 meters. And this is still comparably larger than the size of a typical experiment. So we don't have to worry about axion gradient, field gradient. Now, if there is a strong magnetic field, the axion field can couple with the magnetic field and create the axion electric field. This I call the e to the alpha, proportional to the coupling, the magnetic field, the axion field, and is inversely proportional to the gravity field that we have. And this again oscillate with the omega A. Now, for cavity, if you just put the cavity structure inside and then measure this e to the alpha more strictly. But I want to think about the case when there is a metal in this field. The basic electromagnetic Darwin state that the electric field inside the conductor or metal has to be zero. So the electric field inside has to be over zero. However, outside is the e to the alpha. So there is a very stark discrepancy of the electric field. This is not allowed by the Maxwell's equation. What's actually happening is that there is a traveling wave coming from the metal. This wave coming in, and this traveling wave exactly compensate the exchanges to electric field and make the electric field in metal inside on metal surface exactly zero. Other way you can understand this problem is if you are experimenting with something, kind of the way I understand the problem is this standing wave oscillate, and then this shake the electrons on the surface, and the electrons or any charged particles will accelerate, they radiate their energy, and then this is energy, the traveling wave you see. So the idea of the dielectric haloscope or the dish antenna in general is to detect this traveling wave of the metallic mirror surface, and the rest is pretty similar. This is also with the omega A. So if you detect this power and the T, then in the frequency versus power spectrum, you will see all this monochrome peak above your background. And this is supposed to be proportional to the gamma squared over T. I mentioned that only for the mirror because this is a simpler case, but this is not limited to the mirror. This is in fact more general. So traveling wave emission is more general. It can come up from any boundary between two different media with a different productivity. So in this more complicated example, there's a boundary, and the left side is a dielectric with a relative conductivity 4, and on the right hand side this is a vacuum. So with a relative conductivity 1. The axion induced electric field inside the dielectric, that's this orange arrow, is 4 times smaller than the vacuum. So there is discrepancy of this electric field. To make that up, the traveling wave has to have the vector e to the 1 alpha gamma of the size of half the size of the traveling wave in the vacuum region. So that's the discrepancy. And the H field is the same both inside and outside. So if you calculate the pointing vector equals A equals H, the pointing vector in the vacuum inside the vacuum point this way, and inside the vacuum point that way. So the opposite, the traveling direction is opposite. So based on this principle, we can construct what we call the dielectric haloscope. We want to increase the signal, so we want to introduce more dielectrics and more boundary will emit more traveling waves. So here, multiple signal, dielectric layers, and everything is inside the strong magnetic field, and we detect this traveling wave from the boundaries using either phone antenna or the waveguide taper. A few characteristics of this concept of the say cavities. This is essentially 1D system. There's nothing really setting the limit on the either transverse dimension or this supports the less standing wave. So obviously on the left side, especially if there's no metal canister. On the right, on the longitudinal direction, there is no this receiver, unlike the, for example, in the cavity case, does not reflect. So it supports much less longitudinal standing waves. So this makes this significantly reduce the possible high order modes inside the system. So this may avoid the mode cluttering. This is what it is. So the system is intrinsically 1D and easier to scale, so we can implement the much larger volume. We can also use the constructive interference of the different sources. So if you position the disks level, it can be amplified. You can boost the signals from different boundaries by constructively interfering them. And if you want to scan the next frequency, you simply move the boundaries. So here is an example of what's achievable and the frequency versus the what we call the boost factor. This is how much the power is boosted or enhanced from a single mirror case. So this is multiplied by the area of the mirror is equivalent to cavity's Foley factor multiplied by volume. In the ideal case, when we make these discs out of lantern aluminum with a conductivity about 25 and use 80 of discs, and we can boost the power by a factor of 100,000. And if we have a large area, for example, 1 square meter, then this sensitivity is a system is sensitive enough to detect the PCD accidents in 25.
So this is the case when you have them exactly aligned.
Yeah, this is a similar. This is a similar. This is yeah.
Why it's supposed to be a similar case?
It's from the different. It's from the different modes. I'm not going to talk about it, but if you can imagine this can have a different spatial mode. So this is okay. Yeah, I can talk about that in more details. Interesting.
I have one more question. So is it derived by considering the tuning?
Sorry.
So is it derived by considering the tuning mechanism, or just a single state of the heavy disks?
This is a simulation, so simulation don't really consider tuning. Yeah, just assume every disk is a perfect position, then without any flatness or the surface roughness issues. Yeah. It's ideal case. So this is the MADMAX collaboration. We want to build a dielectric haloscope that can detect the UCD axion in the frequency range of about 20 gigahertz. Right now, these are mainly German experiment. We have 10 collaborators and also from Germany, but we also have the collaborators from the France, Spain, and yeah. And this is the predicted sensitivity of the MADMAX experiment, the final MADMAX experiment. So we want to cover the range roughly about 20 gigahertz where the cavities stop, and we want to go above about 100 gigahertz. So this is the light cyan is predicted sensitivity of the prototype system that we are building right now with a 20 disc inside the morphogo magnet with a 1.6 Tesla, and this is the predicted sensitivity of the full magnets. Now, shifting gear a little bit, I'll go back to the lab and talk about a small project that I'm working on. So, does it really work is a question, obviously, without this really grand scheme. So, we have to prove that this idea is not crazy and feasible. To really answer the question, I begin with a small and a simple dielectric haloscope. So, this is a schematic idea of the one disc and 3 sapphire discs with a 100 millimeter diameter. First, we want to know if we want to how to build one, which sounds obvious, but trivial. Want to measure the reflectivity and then compare it with the simulation. This is the only way you can actually tell if your system behaves as expected, because you cannot actually create the axion like axion distillate field. Then the third question is to understand the noise. Unlike the cavity, I will explain a little bit more later, but in general, dielectric haloscope is more reflective. So this noise behavior will be a lot more complicated. You consider not only the thermal noise from the system, but also the amplifier noise, and this is interfering with itself. So it's complicated. So understanding the thermal noise behavior will also confirm that you understand the system. So the obvious question is how. The obvious first question is how do I maximize the exchange radiation with these two disks?
What is the distance here?
Sorry? Distance
between two.
Just trying explaining. I'm not going. Well, I can give you the exact numbers later, but this will be very boring. But the principle is more interesting. So before I understand it, I ask you to remember the Hertz dipole antenna from your AM class. So if you have a small dipole antenna and you drive the antenna with the electric field, this is the power the antenna radiates, and looks a little bit complicated and daunting, but if you just look at it carefully, this is nothing but the Ohm's law. Power is resistance multiplied by 1/2 of the current. And this resistance is called the radiation resistance of dipole antenna. And again, this looks really complicated, but this is only because of the geometry. If you think about the simpler geometry, for example, infinite plane antenna, this is simpler. So if you stack all infinite number of dipole antenna, both horizontal and vertical, you can create the electron beam, just drive it with an electric field E source. Then you radiate into gamma, and the power you radiate is simply into the source squared by the 2 over free space impedance. Now is free space impedance of 377 ohm. Now, you simply change the voltage source from your voltage generator to the axion induced electric field, and this equation becomes this one. And this is pretty simple, and looks like there's only a few things you can actually try. You can either increase it into the alpha by bringing stronger magnet, for example, or you can decrease the free space impedance. How? This is how you do it. This is what you do with the dielectric. The purpose of dielectric is actually to transform the free space impedance to the lower impedance, so we can extract more of this electric field from the mirror. This. Normally, I don't want to know how you avoid the technical details, so I just prepare this slide. So, if you're familiar with the quarter wave transformer, this is what I call the quasi-quarter wave transformer, because our dielectric is never perfectly quarter wave. So here's the schematic. If you have a load resistance, in our case, free space, this is not, and you want to match it to your generator impedance, in our case with metal, then you bring a transmission line with the impedance as Z1 and the quarter wave length, and this is how this is related. So in normal cases, you have a freedom to choose this impedance matching section. So you choose the Z1 to be square root of Z0 multiplied by Z2, and then corresponding quarter wave length. In our case, we want to match the free space impedance to our metal or the mirror using dielectric. So it's not perfect. We cannot change the intrinsic impedance of the dielectric. And we only have to live with whatever thickness we have, because we cannot change the dielectric every time we change the frequency. Okay, so our impedance transform is not perfect, and this will end up somewhere in the middle, but this is okay. We can repeat the transform. Okay, so this is it. In terms of Smith chart, for the hardcore people, this is the Smith chart of the Smith chart that normalized against the standard free space impedance. So here is the so the red star is the free space impedance, and the blue star is a simply short or metallic area. The green circle is a standing wave simple gamma equals 3.3, 0.5, and 0.7 circles. So this just means if you keep adding the air distance, then you just move around this one. So nothing interesting happens when you just move around the green circle. However, if you move on the different media, for example, sapphire or dielectric, which has the intrinsic impedance about 1/3 of the free space, these brown circles are the standing wave SWS circles from the sapphire. So if you add a sapphire and then you add a quarter wavelength of a sapphire, this will transform the impedance from the red star into the here. And then you decrease you effectively move the matched case to closer to the short. You start the sapphire diode here and then move with air. So this will not change the reflectivity, and you just move here. Then you add another sapphire. This will bring the impedance closer to the short. then you repeat another with air. So if you do it multiple times, then you can quickly change the impedance of the free space close to the metal impedance in the middle. So this is how you change transform impedance and then impedance. Okay, maybe let's do technical one. I think. So this is when I try to explain this concept, unless people are outside the axion field, people find it a bit confused because they haven't really thought about the impedance matching since they're here in class. But I found this nice story will probably give a better intuition. It's like acoustic impedance match. I read a story. Fantastic story I read. So elephants, if you look at them, their ear is actually not very good at hearing. If you just look at the shape, this is actually optimized for how they can hear is actually they can hear from the ground. They basically touch the ground, and this is much more effective way to hearing through the air. And this is a great example of the impedance match. This is not really acoustic, but this is a nice story. So yeah, moving on. So basically, okay, going back to the question of how do you define the actual spacing between them? So like in our case, I have to live with sapphire and then 1 millimeter thick. So this will transform the free space impedance to somewhere here. It's not exactly quarter wavelength, as I mentioned. Exact quarter wavelength will be about 1.3 millimeter. So then if you stop here, then you have to rewind it back to the open side along the air. So this is how you define the air length.
So in this process, I'm sorry, what actually changed in the physical system?
The electric constants?
No, dielectric constant doesn't change. Dielectric constant is already fixed, and you have to live with a fixed length thickness. So the electrical length of the your dielectric is not exactly 1/4. It's not exactly quarter wavelength. But it's something. If we were like exactly quarter wavelength, then you will be end up here.
Okay.
But you are not quite there. And then you have to compensate it. So you have to compensate the rest with the air. So first you need a quarter wavelength of air, but there's a slight offset between this and this one where your dielectrics end.
So you add the addition, you need move or add the dielectric to the iterations.
Yeah.
So you're changing the distance between the disks, is that?
Yeah.
You check the distance?
Distance for the mirror and dielectric.
Yeah, between the dielectric.
What is the gain? How much do you gain doing this?
What do I gain in terms of a boost vector?
Yeah.
Yeah. So this is the actual setup. Like I said, this is a mirror and the 3 sapphire discs stacked together. And I want to keep the exact spacing, so I put the aluminum rings between them. Then everything is stacked inside the stack and inside the tube. And there is a parabolic taper which basically plug the signal into a standard waveform. This is a cross section of the signal. So this is sapphire, then ring, sapphire, ring, and so on. Yeah, and this taper. And this is the actual construction. Because this was basically proof of principle, we wanted to understand that we actually build our system. So we developed the tuning. So this is the disk position space, and we will operate on linears and eigenvalues. The what we call the boost vector is about the vector about 1,000.
This is beta or beta square?
This is a beta square power boost. Yeah. And it's a long flood. There's also the reflectivity diagram. The simulation predicted about 1 + 1 dB drop due to the main loss at the mirror. So this is why I said this is a very reflective. We can make it. We can, or again, in terms of cavity, we can critical couple it, but now this is just early stages, so we don't want to make the system too sensitive.
So this is a measurement.
No, this is a still simulation.
Yeah.
Yep. And this is a measurement, reflectivity measurement and the room temperature. The frequencies versus the reflectivity. The top is magnitude, and the bottom is group delay. We care a lot about group delay because this is visually gives you a better idea. The frequency we want to boost is about 19 gigahertz. So this is our frequency peak, and this agrees reasonably well between the data and the simulation. The structure is pretty simple, very complicated, but we find our peak. Most of the other peak is from the mode missing instead of taper. Our taper was limited by the size we can fit inside the capacitor. If we can make the taper a lot longer, then many of this will go away. In the magnitude diagram, this is our peak and data versus data simulation. The data and simulation. The simulation predicted about 1 dB loss, and we measured about -2 dB. This is a little bit outdated. This shows -3 dB, but the latest measurement shows -2 dB. So this is not bad. It doesn't critically lower our boost temperature. Just a side note, initially we saw much larger loss. It can easily go below -10 dB, and then this turned out to be lost the rim of the characteristics. And I solved it by applying gold layers on the rim of the substrate.
How do you identify its immunity?
Sorry?
How do you identify its immunity? According to the group delay diagram.
Yeah. How do I identify?
Yeah, how do you say it's immunity?
I can change the system division. For example, I can just press on the mirror and slightly deform it, and this one, this shift a lot. Yeah. After playing for a of time, this becomes obvious. So this is activity right now. We understand system the room temperature, so we are now the search. We're taking this is an ongoing activity over the holidays, so we'll collect the data for 30 weeks. We also measured the reflectivity in the liquid helium temperature at 4 Kelvin. And this is the setup, and this happened about October, and this is the result, and this looks very promising. Initially, we had some other issues with the pressure measurement, but with this dry setup, I see on the slide shift of the frequency to the higher frequency between the room temperature and the 4 Kelvin. And this is fully due to the thermal projection of the aluminum. So yeah, so this is successful. So we are taking data and then some other. We've been very happy with this closed booster proof of principle system. So we're taking data and we are thinking about ways to upgrade it. For example, this wasn't fixed, so I cannot tune it on the in situ. But we can tune. There are some ideas how to tune it. For example, we can use piezo motor or we can load the system with helium gas. This is not very used in the low frequency region, but this is doable in our high frequency region. Helium is reasonably gaseous at the very high frequency. And as we are thinking of other variations of the dielectric haloscope.
Could you tune the spaces along the discs with a single cage, or do you have to tune each of these discs?
Sorry?
At the room temperature? I'm curious about the tuning system at the room temperature. So can you control?
Right now in the room temperature, we are not considering tuning. Yeah, if you want to tune it, then we have to just disassemble and then swap all the rings. Which is not terrible, but yeah, it's not as good as a tuning.
When you tune it, you move all the discs.
How many tuners do you?
For small range, you can tune. You don't have to move the whole disc. The really critical part is between the mirror and the first disc. So if you just move the mirror slightly, then this shift a lot. Of course, you'll lose some of the boost vector if you move too far. So there's a you can say there's a fine tuning and rough tuning roughly. You can do fine tuning with the ideal gas or the payload actuator.
Then thermal contractions can be on the control.
So far, yeah, this is this thing we this is this was I didn't really have a chance to exactly overlay with the simulation. Simulation itself is another effort. At least in the terms of the amount is corresponding with the 1D process, 1D expectation.
But here, because you're using sapphire, which is direct constants only 10 or 11, which is fairly small for your experiment, such that you're moving the needle itself to change the frequency. But in reality, you are supposed to use very high direct constant material, which basically in ideal cases this is supposed to be the same as the conductor, right? So in that case, you're moving all the things is very important.
In the large frequency range, we have to move all this. No, I'm talking more about the fine tuning. For the much large, if you move to the 1 gigahertz, then you obviously have to move everything. Yeah, but we are talking about using other alternative dielectrics, but right now we are focusing on sapphire. That's already pretty good. Yeah, you gain maybe 10-20% more boost vector using polyton antenna, but this comes with its own price, so it's really helpful. Yep. And so this another problem we're doing is that we want to scale up the system. So this is the 20 millimeter system closed booster. Basically, this is the diameter is 200 millimeter, and we can stick to 8 discs, but we'll probably need only 3 or 4. And then instead of using the spherical taper, we use a lens, and this is designed by the UK company, and just probably right by now. So we're going to play with it and
Is it broadband booster?
sorry.
Is it broadband booster?
The bandwidth will define how you arrange the disks. Roughly, this is certainly broadband if you think about the cavity. But it's not as real broadband as the breadboard. So and then because we are successful with the room temperature close booster, we are going to use it for the experimental search, and the MADMAX made an agreement with the CERN to use their morphogo magnet. This is a morphogo magnet, and this provides 1.6 Tesla dipole field. The door is about 1.6 meter, right? So we'll bring it in and then measure the signal in coming March, and there is a space shuttle. We initially planned for the initial travel in January, but this was cancelled because of COVID. So and this is the predicted sensitivity of the morphogo measurement. So axion mass, and so about 19 gigahertz, and this is axion coupling. There's a Castor limit and the QC lines. The morphogo will slightly punch through the Castor limit. This is already exciting. It's small, but this is for the first time. And if this is for the case with the signal to noise ratio of 5 and the system temperature, basically room temperature plus the amplified noise, I think we are already doing better than this one. And just 4 days of measurement. If I go a little bit ambitious, and if I add a second, another disk, the 4-disk system is exposed to the critical coupling, and put it in a cold nicotine biostat and a small permanent magnet, then this is how this is pretty resistive. It can jump on the board. So, moving on, we're talking about the current activity and the collaboration. It's mainly for the 200 plus the prototype. So this will be the technical test platform of the MADMAX. We want to test the disk conditioning with a piezo motor plus laser interferometer in the cryogenic temperature first, and then inside the high magnetic field. So this is the setup now being built by the University of Hamburg. They'll build, I think they built it right now. So they will bring the system to the CERN this winter, and then test it inside the Morphogo next winter.
Actually, what here 200 means?
200 is diameter.
Diameter.
Yep. And this is the, if we are successful with the 200, this is the prototype. This consists of a 20 300 millimeter disc, carbon sapphire. We move them with the piezo cushioners and the laser interferometers. So that's the first. That's the what we call the prototype booster. We house them inside the liquid unified step. And there's a focusing optics and the one of them to collect the signal. So we'll first test it, assemble it and test it, and make sure that we can actually test it. And then once we are confident, then we'll bring it into the Morphogo again for the DFG recently funded the cryostat, so this will be basically the University of Hamburg actually put the cryostat on tender. This will be delivered within a year.
So you plan to fold this entire system inside the magnet?
Yep.
Oh, okay.
Yeah. This is 3 huge magnets. I think the ball is actually larger than the final MADMAX board. Build is of course weak. And one critical element of all this technical R&D is cryogenic piezo. So we want to move this will basically sit on this piezo actuator move along. And so far we tried a couple different models, but not very successful. But recently we made a successful test with a new piezo cushioner. This was developed by JPE. I think I heard that Chang also has experience with it. My colleague Dagmar tested the piezo motor at the liquid helium that cryostat, and it was moving very slowly, but pretty enough. So confirm this was operational. So she's moving the setup to the ARC2 magnet, which provided by Tesla. This was scheduled actually this autumn, but there was some conflict. This is pushed back, but will happen soon. Another, of course, important R&D item is amplifier, and this is our main interest is to develop a traveling wave amplifier that works above. So this is mainly driven by the Neo Institute in Grenoble, some of our collaborators. They published 2 power working in the up to 5 gigahertz, and has a noise temperature factor 2 of the. So they are designing the system that can work up to 10 gigahertz. They are going to send the students so that they can help them with the design. And yeah, this is a final MADMAX. It's a bit far in the future, but this is a schematic idea how the system will need to cover QCB axion. You have the booster that consists of 80 discs made of non-tan aluminum, and the diameter is 1.25 meters. This is housed inside the 9 Tesla dipole magnet, and we collect the signals from this. The focusing mirror and the SD4. So the key item for the MADMAX, full MADMAX is this humongous magnet. It's not only dipole but Tesla, so this is one of the strongest magnets in the world. The design is ongoing by building a Planck Institute, and this is Clay, and this is the design. Like Tesla, they did 1.3 meter bore. This is 6 meter long. This is planned to be housed inside the Hera 1 North Pole of Daisy. So this is the current state. So this is Daisy ring and Hera Pole is here. If you go inside, this is the Hera 1 solar magnet. We'll take it out and bring our magnet in, and we'll reuse the yoke of the magnet. We'll drill holes here so we can put the booster inside. And this design is ongoing. It's on parallel. They recently proposed to use the level titanium copper jacket, which is a slight variation of the one used for the ITER. And this is supposed to be better. And they just tested those quench of this new conductor, and this was successful. So this is a long, hard process of steadily moving on. And again, this is project sensitivity to the MADMAX. We will cover the range post-inflation excitation range of about 20. So here's the summary. This is the document candidate, and we are interested in detecting axions of 30 microeV, and the haloscope is a policy to support time to the standard system. Nonetheless, we are very successful with the small first prototype and protocol principle setup, and we want to do the first digital data and the commutator, and the prototype will continue until 2024 or 25. And the question is it really filled or is it empty?
Thank you.
Thank you. Any questions?
It was very interesting talk, and for the MADMAX for the MADMAX prototype and with a low temperature piezo positioner, what would be the dynamic range of the search range? The dynamic range, the scan range.
I don't remember the exact number, but roughly we want a range of on the order of meters or even 10 meters. This was another challenging requirement for this piezo positions because we don't really ask for such a wide range in cryogenic conditions. Yeah.
You said the order of meter?
Yeah.
It's long.
No,
Cubic meters.
The only feasible design is basically a stick slip design, which in principle doesn't really have a range limit. Yeah, it's very technical.
Maybe one centimeter is like it can be in a kilometer.
But you need a
It's because they're probably one different case.
So what is, can you go back to the picture?
There's one.
A little bit more. Back. So for this, you assume a certain noise temperature. Is 8K what I read correct? That's what you assume?
Yeah.
8K. So if you had a better noise detector, you could do much
I
better.
think this is assuming the 4 Kelvin helium cryostat. So if you use the helium-3, for example, helium-3 cryostat, then there's a room for the super applied cryostat, then this can be lowered. There's a little room for it.
Right.
You just don't want to use a direction refrigerator.
So what is that band in the middle?
This is when we use this. So, like I said, the nature of the haloscope depends a lot on how you position the disc. You can push on the one extreme. You can push it like so, position so they give basically like a cavity. On the other extreme, is very sensitive, but this becomes extremely unstable. If you use some other what we call the transparent mode, then this becomes much more broadband and stable. So depending on this configuration, your solution can change a lot. So it's the wide range is when you have a more conservative, stable configuration.
Right.
Any other questions? Other questions from online side? I remember you mentioned that only one of the only slides you cannot calibrate your system using sort of fake action signals.
Oh.
Did I understand correctly? And then you only measure your measurements can be confused by reflection and refractive measurement and then so.
Yeah. Well, the basic idea is that you cannot put such signal in the lab.
I mean, why?
It's simpler for resonant cavities because your axion is the mode is the same as the mode you accept with your DNA, but for the haloscope they are slightly different. So yeah, there's a.
You showed some antenna, right?
If you
dipole antenna and then why not that different?
If you then have
continue.
Yeah, you can disrupt also the field node, and this is a tricky question. Yeah.
And for example, your prototype with 3D scale, it's a very small area, and then you can.
For 3D scale, there's much less power, yes, because this is much closer to the resonance. So we don't really worry about it. But if you have a much more bigger complicated system, it is big problem there.
Any other final comments and questions? Otherwise, let's thank the speaker again.